Okay, this is section 12.4, testing for a correlation coefficient. Here's problem number 2 in that series of videos there for that section 12.4. Sorry here. This one says a sales manager of Copier Sales of America has a large number of sales throughout the United States and Canada and wants to determine whether there's a relationship between the number of sales made in a month and the number of copiers sold in that month. The manager selects a sample of 15 representatives and determines the number of sale calls each representative made last month and the number of copiers sold. Use a 1% level of significance to determine if the number of sale calls and copiers sold are correlated, and assume that the normal number of sales calls made and copiers sold represents the bivariate normal distribution. All right, so starting off with this example here, this is problem number 2 for section 12.4. So go back and see the first video that I did with the giant sequoia trees. That'll answer probably a lot of questions. I'll go through this a little bit faster than I did with that one. So starting off here with the populations, just going on with that theme, there is population 1 and 2, the control group, the experiment versus the control group. Here for that one, that you want to say for the experiment group, population number 1, that there is a correlation versus that there's not. So here we're looking at the set of all sales representatives or sale reps in which there is a correlation. So that's important there. In which there is a correlation between the number of sales made and copiers sold, period. So that's going to be our first set there for the population number 1, that there is a correlation, versus population number 2, that we're going to change that just ever so slightly and say that there is no correlation, making those two very distinct in that slight change there. It's pretty much black and white in that case. However, for the research of null hypothesis here, starting off with a null hypothesis, we want to assume that rho is equal to 0, versus here up there at the top it's stated that there is a, so again here a correlation. So here let's assume we have nothing, assume no correlation, but down below let's try to prove that there is, prove we have something, prove there is a correlation. And the reason why I just want to prove that there is a correlation, let's go back up to the top and look at that here. And there I have it in bold, that there is a correlation. Along that we're going to look at just a second the level of significance up there. So this is not saying that it's negative or positive. We want something here. As long as I can say here that rho is, identifies with, either being -1 or +1, we're great. So for a correlation, it's not being specific about being one directional. You can go either way. You can prove it's negative, like a negative correlation, or positive, as long as there's something there. So let's keep that in mind, as that, again, we're not being specific here, and that's why I went with the not equals, the two-tail case. We'll look at that in just a minute. Part here two to verify, so we want to assume or have proven that both x and y are bivariate normal. And because that's the case by assumption, we get to use the t-distribution. So for correlation, we have to prove that our variables are bivariate normal in order to prove that. And because there's a theorem that states because they are bivariate normal, therefore both x and y are independently normally distributed as well. So, and all that other stuff. But got to start there first. All right, so let's go and grab here the t-distribution, always associated with, anytime we're doing this with correlation, go along with t there. But of course, a few preliminary stuff here to start off with. Alpha is that level of significance. Up there at the top, it's going to state 1%, which is equal to 0.01. However, we're going to come down here and say that we want to prove a two-tail test. So therefore, what we're going to end up wanting to do is take our level of significance and divide that by 2. We want to share that on both sides. So divide by 2, therefore, on both the left and right side, as you folks may know, that's the 0.005. So on the left side, and also rather on the right side using GeoGebra calculator, place in both of those numbers. I only do that because of the two-tail. And I usually get the question, teacher, when do I take the level of significance, divide that by 2 to share it? Only with the two-tail case. And I went with two-tail, obviously because they weren't being specific because of the not equals. So not equals right there implies two-tail, always. Down here at the bottom, degrees of freedom for correlation, df is the sample size minus 2. So since we have 15 reps sampled, 15 minus 2 is going to give us a degrees of freedom of 13. So let's plug in those numbers in there, along with grabbing both those brackets, the 0.005, the 13, and both the left and right bracket. So jumping back over to GeoGebra, using that as a statistical calculator to figure out that cutoff point. Let's grab the first one here. Let's go find t. All right, there we go. There's t, student t. Change that to 13. Done. Grab the left bracket there and then place in that 0.005. Okay, done. There's our first lower value. We're going to end up coming with 2 of these, negative 3.0123. And then also for the right side, that's going to be just a sign change, pretty easy there. Place back in that 0.005, and you get 3.0123. Again, both opposite numbers of one another. All right, so let's jump back over here. That is our answer. So T naught equals plus or minus 3.0123. 3.0123. There we go. There, we're going to map these out. And again, on the drawing here, I just want to point out that on trial, we're assuming that there is no correlation, and we're going to try to disprove that. So we want to be beyond these cutoff points here. Here at positive 3.0123, just to the right, just to that one that's that little 0.5% there, and on the bottom side over here, less than negative 3, just opposite sign there, 0.123 there, just over there. So if we're going to be beyond those cutoff points, we have proven statistical significance. Let's go ahead and look at the sample and see what we could reveal. Were we able to show that with the 15 reps? So let's go, slide over here next door and write that down there for the stats there. Sample size is again equal to 15, so we have the 15 reps. And then their R value, the sample correlation coefficient, R. For this problem, let me just going to go write this down. I'll show you where I found it. 0.6939. 6939. And again, on that scale, we want to be either close to -1 or +1, where 0 is in the center. So here, we're on the positive side, but a little bit beyond, maybe closer to 1, but again, are we close enough to +1 to prove that we have something here for a value r? So let's go ahead and standardize that number, slide over here and turn that into a t-value, back to step number 5. And again, the formula for that t is equal to, you're going to take that r value and subtract 0 from it. So starting off with parentheses here, 0.6939 minus 0, you certainly don't need the minus 0 there, divided by, in parentheses again, 1 minus 0.6939 squared, close parentheses, divided by 15 minus 2. And usually in a lot of cases I just write down the 13. I don't necessarily write down 15 minus 2. You could just do that in your head. Alright, this is where we want to grab a good calculator. And for the last problem, I tried it out there with a scientific calculator. I got it. We got it figured out. But certainly some of these better ones, like a graphing calculator, or I'm going to use Mathway just a second to grab that number, that standardized number. Let me go write it down just for reference here, that we can go and double check and see that we get this. But the answer for part 5, the standardized value is 3.4745. 3.4745 is that magical number there. We want that. We can kind of automatically, if you're looking at this, you know this is just right there at significance. It's right off past that cutoff point right here. So that's good as far as what the researcher wants to show. But let's go and see if we go and find it. So let's jump back over to GeoGebra with order of operations. Sorry, not GeoGebra, but Mathway. All right, so let's go and try this out here. Let's go and clear out the problem. Okay. All right, so starting off with parentheses here, we have just the r value, 0.6939 minus 0, close parenthesis, divided by square root there. In the square root, again, you've got another parenthesis, but in this case, if you want to, you could put a fraction. You don't certainly have to, but I'm going to put here 1 minus that r squared, 0.6939 raised to the second power, cursor 1 over to the right to close parenthesis then, and then divided by the degrees of freedom of their 13. Let's go ahead and enter that in. And there it is there. Again, verifying the 3.4745 rounded there to 4 places. Alright, so jumping back over, let's go back to the problem. That's our cutoff point there, verifying that for our answer using anything like with a, in that case with a wide screen, a bigger screen than just your standardized scientific calculator. Kind of limited on its capability there. So anyway, for this problem, we know that we have a rejection of the null hypothesis, which is great. We are able to show that there's some sort of correlation there dealing with those reps. And we should establish the correlation. There is a relationship between how many times they're busting themselves on the phone, making all those calls, selling those copiers. Let's come back over here for the p-value and find that for t. So this is where we certainly have to be careful. Because we don't have a left tail, right tail test here, we have a two-tail. We're going to have to take this value and multiply it times 2. But I'm looking back over here, and only because you look back this part here for part number 5, because this is positive, that implies you want to go to the right, shade right. If that number was negative, we would have shaded to the left. So because that's positive, I'm coming over here, and now I'm going to go to the right, or in other words, greater than that number, 3.4745. And then take your answer and multiply it times 2. Let's jump back over to GeoGebra and find that probability. Okay, there we're at the student T. Got our 13 in there. Right bracket. And then place in that standardized value 3.4745. Click back the right box there. The 0021, that's her p-value, 0.0021. Then we're going to multiply it times 2, forcing it to be on both sides, forcing that to be a two-tail case. And then we can see here that if you just go ahead and double the 21, you get 42. So we get 0.0042, or in other words, of course, that translates into 0.42%. 0.42%. That's certainly smaller than 1%, and that verifies that we do have a rejection of the null hypothesis. All right, so that'll do it. So if you're a manager there, you want to verify and report that, yeah, that we do have some sort of correlation here. In this case, the more sales calls made, the more copiers are going to be sold. So that'll do it here for this example here, and showing that there's, and proving that there's a correlation in this section 12.4, testing for a correlation coefficient.